Just a quick synopsis, graphs of polynomials. Uh, let P of x equal x minus, well, what you see here. I'm going to read it all to you. We can multiply these out. We're going to get an x here, an x here, and an x here gives us an x cubed. We're going to get -5 times 2 is -10 times 6 is -60. And we're going to get some stuff in between. It's fairly easy to figure this out, but you really want to write this out in detail using the distributive law to multiply this by this. Don't use that F word thing because it doesn't work for trinomials, for example. And then you multiply the result of this, which is quadratic, by this, and you get the cubic. And I think these are the numbers you come out with, but I don't know for sure. I haven't multiplied it out to check it. Something like this. And I think that's probably right. So this expression that you get here from this equals -60 if x is 0. Now you can verify that if x is 0 up here, you get -5, 2, and 6, which multiply out to -60. So both ways, it's easy to figure out that you get -60. And it acts like x cubed when absolute value of x is large. That is the long run behavior. Far to the right, far to the left, the magnitude of x is large. And this acts like x cubed. Why? Because if you make x large enough, x cubed overwhelms the value of any multiple of x squared, much less any multiple of x or any constant number. So we get 3 points on the graph from the zeros. In other words, if x is -6, y is 0. That gives us a point -6, 0. We get -2, 0. We get 5, 0. We sketch a little dotted graph just indicating the x cubed graph. And we have the point 0, -60, because when x is 0, y is -60. We know then that for large x, this thing's going to act like x cubed, which goes down very rapidly as you move away from the x-axis. If you move far enough away, this graph and this graph will become very nearly the same. Similarly, over here, the x cubed graph goes this way and goes rapidly upward. So this graph has to go rapidly downward as you move to the left, rapidly upward as you move to the right, and it has to go through these 4 points. Well, the most direct, smooth curve you can draw looks like this. And that's a fairly good facsimile of the graph. Now, in analyzing it, all I said, for large x, long run behavior, you get x cubed, going to act like x cubed eventually. Nearer to x equals 0, these zeros take over and you have this wiggly behavior. Okay. Now, a graph of this polynomial, just like the other one, the same factors. No, sorry, that one's cubed. We don't want it to be cubed. And what am I doing here? Okay, that's not it. This is going to be it. Okay, getting out of sequence. We've got to get to that one, but not yet. And we don't want that one. Yeah, okay, here we go. Okay. Now, what I started to say before, now I've got the right graph. If we have this function, it's just like the other one, except you have a square on the x plus 2 term. And that square makes a difference. Among other things, if you multiply these out, x plus 2 quantity squared is not x squared plus 4, incidentally. Make sure you get over that if you think so. It's x squared plus 4x plus 2. But you're going to have an x squared here, and an x here, and an x here. Well, that's going to give you an x to the 4th. And then you're going to have a 2 squared, which is 4. You're also going to have that 4x. Don't forget about it. But you're going to have 4 here, -5 here, 6 here. That multiplies out to -120. So we know the overview of this. The end behavior is like x to the 4th. And x to the 4th has a graph that looks a lot like a parabola, but it's flatter down here and steeper out here. So the overall behavior of the graph in long run is going to be that of the fourth power function. The zeros occur at 6, 2, and 5. And as you see, we've got a zero that acts like this at 2. Okay. If you try to go through a zero here, here, and here, the way we've done before, and if you start high, which you have to because of the x to the fourth, you're going to come down through here, up through here, and down through here, and you can't get back because there are no other places where this thing goes through zero. Well, that's not going to work. Also, you get a positive y-intercept when it should be negative. Okay. Well, the key to the mystery, there's a rule for this, but let's look at the reason for the rule. It's not that hard to understand. The key idea of how this graph behaves near x equals 2, because that's where the monkey wrench gets thrown in, is that the graph acts like a vertically stretched and maybe reflected, and it is reflected in this case, graph of the x plus 2 quantity squared function, which is just a vertically stretched x squared graph shifted 2 units to the left and may be reflected. Now, why do I say this? Well, if x is really close to -2, then the only thing that has significant changes is the x plus 2 quantity squared function, in the sense that the x minus 5 stays close to what? -2 minus 5, which is -7. The x plus 6 stays close to -2 plus 6, which is 4. -7 times 4 is -28. This times this stays close to -28 if you stay very close to x equals -2. However, this has a parabolic shape, as you know from vertically stretching and shifting your basic squaring function. Okay, well, that's the reason you get this parabolic shape here. Now I drew a little parabola here and a little parabola here and a little parabola here and a little parabola here. Why did I do that? Because I know that this thing is going to behave like a parabola at x equals -2. And the parabola will be a vertically stretched or compressed x squared graph. I chose to stretch it. So here we have it, and here we have it. But we could also have reflected it with the negative in front of the x plus 2 squared, which is what occurs because, as I said before, this acts like -28 times the quantity x plus 2 squared. And that's going to be it's going to be 28 times your x squared graph. In other words, vertically stretch your x squared graph by a factor of 28. And because of the negative, then you have to invert it. So you get this. Now you shift it over to the left and you get this shape. I didn't quite hit the vertex right, but you get the idea. So there it is. So there's a statement. Near x equals 2, this acts like a y equals x squared graph, vertically stretched and may be reflected 2 units to the left. Okay. Now we want this, but not yet. And now we want to look at, here it is. Now, what if your x plus 2 is cubed? Well, the same principle applies. This is just, these numbers stay pretty much constant if you stay close enough to x equals -2. And these numbers still multiply out to -28. So it's like you got -28 times the quantity x plus 2 cubed. Well, that's the cubing function, basic cubing function, which I've sketched in orange here and in purple here. So this would be your basic cubing function, and this is your basic cubing function reflected through the x-axis with the negative sign. And also vertically stretched by factor 28. So we have this and this. Then you shift that 2 units to the left because of the x plus 2. And of course, you have to understand transformations and why they work. So it's reflected and shifted 2 units to the left. So the behavior is like this as you go through -2. Now, through -6 or through the 5, the graph goes through, and locally, if you look at it very close, locally, it looks like a straight line. If I just zoomed in on this, so this is part is all you can see, you wouldn't be able to see much curvature in that line. It'd be almost straight. Similarly over here. So in any case, your x equals -2. The graph acts like a multiple of y equals quantity x plus 2 cubed, actually like -28 times x plus 2 cubed. And that's like -28x cubed shifted 2 units in the horizontal direction. In other words, 2 units to the left. There it is, as I said it. Okay, so not ready to do that yet, but I'll set it up. I'm missing something. Maybe not. Maybe I want to be this one. Okay. Here's another graph. Now I'm showing you what to do if you're given a graph. So we're given a graph here. There's zeros here, here, and here at the indicated points, and a y-intercept here at 0, 40. At each 0, the graph is locally straight. Straight line, straight line, straight line, at least very close to a straight line as it goes through the x-axis. So taking all that information, let's look at what we've got. Okay, so what is the equation for p of x? Well, it has to have factors, has to have factor x plus 5 if it's polynomial, because otherwise it wouldn't go through -5, 0. Has to have a factor x minus 3, so it can go through 3, 0, and x minus 5, so it can go through 5, 0. So you know then that p of x kind of has the form x minus 5 to some power, x minus 3 to some power, x plus 5 to some power. Well, since the graph is locally straight through each 0, the exponent of the corresponding factor is 1. If it was 2, it would be parabolic. If it was 3, you'd have a cubic looking graph. A factor 1 is like x to the 1 as opposed to x squared or x cubed. And x to the 1 is just a straight line graph. Y equals x gives you a straight line graph. So we conclude here that these 3 exponents, because of the way the graph goes through the x-axis in a straight line, all have to be 1. So maybe p of x is x minus 5 times x minus 3 times x plus 5, but it turns out it's not quite so. We can check that. If it has this, p of 0 would be 75, not 40. Okay? And it has to be 40 because that's your y-intercept. If x equals 0, you should be getting 40. You're getting 75. That's a little too big. What do we do? If you let p of x equal 40 over 75 times these factors, then it's going to be 40/75 of 75 when x equals 0, and that's going to be 40. Okay, so say if If P of X is 40 over 75 times these three product of these three factors, then P of 0 is 40 over 75 times negative 5 you get here, negative 3 and the 5 you get here when you substitute X equals 0. These three multiply out to 75, negative 75, out 75, okay? And 40 over 75 times 75, just 40. So there we have it. Now, if your graph looks like this, what are you going to do? Well, you got a 0 at negative 5, at 3, and at 5. The 0 at negative 5 acts like a parabola. So, you have an x plus 5, which will give you 0 at negative 5, but it has to be squared, or it wouldn't be giving you a parabola. And at x equals 3, the thing levels off and goes down like this. Not particularly well drawn, but you get the idea. That's the way a cubic function works. X minus 3 quantity cubed. Now, I'll mention that this behavior could be a fourth power or a sixth power, some even power, because that's the way the even power functions behave. But they get flatter and flatter and steeper as you go into higher powers. And the cubic function could really be a fifth power or seventh power, some odd power. For the purposes of this course, we'll stick with first power, second power, third power. Okay. So we go through this 0 as a parabola, through this 0 like a cubic function, and through this 0 like a linear function. That means that our polynomial is going to be some multiple of x plus 5 squared for the parabola, x minus 3 cubed for the cubic function, and x minus 5 for the linear. Thus, P of x is some multiple of these three factors, and A is going to be your multiplier. Now, just like in the previous example, we found that you had to multiply by 40 over 75. Here, we're just going to put A in there, and we're going to solve for A. We could have done that on the other one. We've still gotten 40 over 75. Okay, so here's our polynomial. P of 0 is supposed to be 40. But of course, P of 0 is A times 0 plus 5 is 5 squared. 0 minus 3 is negative 3, which is cubed. And 0 minus 5 is negative 5. Well, we figured that out, and I didn't figure that number out. It's 27 times 25, times 125, the 2,700, about 3,300, and actually you can probably do that, 3,325 maybe. Okay, anyhow, that comes out to some number that you can easily calculate by hand or over the calculator. So if P of 0 equals 40 and P of 0 equals this, then 40 equals this. This is a simple equation at A. So you solve that for A, you just divide both sides by this product here. And that's what I've indicated. And then if you don't have time or inclination, be legitimate enough to use a calculator to calculate this denominator, or to just go ahead and calculate the decimal equivalent of this fraction. And I think it come out around 0.0013. Now, when I calculated it, it's probably closer to 0.0012, maybe 123. I don't know about that. But if this is right, and I got a question mark there, you can do the arithmetic. That P of x should then be 0.013 times this, times this, times this. In other words, A is about 0.013, we put 0.013 in here. This is what we get, and there is our approximate polynomial. That's our polynomial. If these points are exact, then that's it. If these points are approximate, in other words, we've estimated these coordinates from a graph that isn't totally precise, then we have a good approximate function. Okay, so that's pretty much it. The video quality on the last one was not good. I want to compare what happens a little later in the afternoon. And this is also a lot quicker than what we did before.